everybody. So now let us continue our discussion. So this week we will be discussing about supramolecular chemistry, which involves recognition of organic cations, organic anions, and we'll be looking at extended concepts of supramolecular chemistry. So till now in the syllabus we will be focusing primarily on cationic response. What is the response of cations to different host molecules? Now we'll be discussing into a different area of supramolecular chemistry, that is those involving anions. But before we proceed to anions, we would like to first take up the interaction of organic moieties, organic cations with a different kind of host molecules. So the supramolecular chemistry of organic cations with host molecules. So we will be now taking some specific cases, because we have by and large looked at cation recognition behavior. We have looked at cryptands, we have looked at ethers, we have looked at lariat ethers, and so on and so forth. So let us now take up different examples. So to start with, let us look at the cryptand. And in this regard, we will be taking different kind of cations, particularly those involving the ammonium types, where R1, R2, R3, R4 are different functional groups, or they can be the same functional groups, and the corresponding ammonium salts of these. So for example, let us look at the cryptand. We have taken the example of 2,2,1 cryptand, where we have looked at n is equal to 1. We can also have n equal to 2. In that case, it will be a 2,2,2 cryptand, and we can now modify this cryptand to form the following molecule. So let us look very closely at this modified cryptand, and this resembles a soccer ball. And what we have now done is we have actually added a set of nitrogen atoms here, and then another arm of the nitrogen atom which connects this nitrogen atom is the CH2CH2 O CH2CH2 spacer. And we can actually now represent this particular soccer ball in the following way. So this has got a tripodal geometry. You can see here, this is also a tripodal geometry. This is a tripodal nitrogen, this is a tripodal nitrogen. And we can represent it in the following way. So, this is a representation of this soccer ball compound where we can see the tripodal nitrogens, and now we will include the ammonium cation here to start with. Which forms hydrogen bonds via N plus hydrogen bonds with the soccer ball. So, now you can see that the ammonium ion binds to this cryptand, and this results in the increase in pK of ammonium ion, that is this particular process where the release of the hydrogen ion has to be done by ammonium ion. So, now because the complexation with the cryptand, the increase in the pK of the ammonium ion is by 6 units. That means now these protons are more strongly held by charge assisted hydrogen bonds, and because of the strong hydrogen bonding the hydrogens are stabilized in this particular complex. Therefore, it is very difficult to abstract this proton, thereby resulting in an increase in the pK of the ammonium hydrogens by 6 units. And therefore, it is very unlikely that these hydrogen atoms or hydrogen ions will now be lost, because the pK value is now increased by 6 units in comparison to the uncomplexed analog. Okay. So, this is one very interesting example where we can have ammonium ion stabilization with the soccer ball complex. Similarly, we can look at binding of ammonium ions with corants. Where we can now draw So, we now have this as a corant, and it undergoes complexation with the alkyl ammonium compound. So, we can draw the nitrogens here. These are the hydrogen bonds. Okay, so you have these hydrogen bonds which are present. And the R is above the plane of the paper, above the plane. So, it sits now in a Pershing geometry. So, this sits actually on a Pershing geometry where now the tripodal hydrogens of N nitrogen, they now interact via the NHN hydrogen bonding, and the R group sits above the plane. So, in this Pershing geometry, via these charge assisted hydrogen bonds, the organic ammonium cation is able to stabilize itself. Now, we can look at some thermodynamic data which is related to the thermodynamic data that is related to the complexation free energies for coherent receptors with ammonium ions. So, let us look at this particular data, and this is with respect to the coherent receptors with the ammonium ions. So, now we will consider here 3 such coherent receptors. This is the first coherent receptor. The second coherent receptor is a naphthyl fragment, and the third one is where we have the methyl group here and the methyl group is now here, and this is okay. So, you see that you get the orientation of this particular binaphthyl unit, and the methyl groups are now above the plane as well as below the plane. So, we have these 3 host complexes, and we can look at the thermodynamic data where we can look at the complexation of these 1, 2, 3 with the ammonium cation with the methyl ammonium and R3C N3 plus, okay, where all the hydrogens have been replaced with the alkyl group. Now, this value is 10.5 and this is in kilocal per mole. For the methyl it is 9, it is 8.3, 9.5, 7.5, 6.9, 8.9, 6.9 and 6.4. So, we can see that when we go from left to right, that is given a particular host. When we start from ammonium to methyl ammonium to R3C plus NH3 plus, there is a decrease in the magnitude of the the complexation free energy. And similarly, when you go from top to bottom, that is when you change the host from 1 to 2 to 3, again there is a decrease in the complexation free energy. And you can see that the decrease is pronounced on going from ammonium to methyl ammonium. The decrease is 1.5 kilocal per mole. Here you can see the decrease is around 2 kilocal per mole. And here also you can see that the decrease is around 2 kilocal per mole. So, there is a pronounced decrease in complexation free energy when the host changes from ammonium to the methyl ammonium. And so, this difference suggests that replacement of H with methyl, and then further on replacement with further CH3, this increases the steric bulk and hence the magnitude decreases. And when you come to this particular third host, that is you have the methyl complex, then there are unfavorable steric interactions with your R, which are connected to carbon. So you can see here that when you have the R, the bulky groups, they will be actually interacting with the methyl groups at these two positions. So there will be severe steric clashes between the R and the methyl groups, in this position as well as in this particular position, and that results in a decreased affinity of the ammonium ions for the host complex, thereby decreasing the free energy change associated with this process. So we can now consider even larger size cations here. We can now consider larger size cations. So complexation with larger cations. For example, we can consider the guanidinium cation, and we can consider the imidazolium cation as well. So let us first consider the guanidinium cation. So this is guanidine, an addition of a proton makes it so this is my guanidinium cation, and for the corresponding imidazole, we have the nitrogen lone pair, and we have the lone pair here as well. So if we add a proton, it protonates the ring nitrogen, so this is my C3 H5 N2 plus. So this is my imidazolium cation. So this can also function as an organic guest molecule, and we can now look at the complementarity, the electrostatic complementarity between guanidinium and the host. So let us look at this host, which actually is a 27-membered corand. So in this 27-membered corand, let us draw the structure. We have the R groups here. We have the R groups here, and we have got the R groups here. So we have got this 27 membered, and 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 oxygen atoms which are present. So we call this the 27 crown 9 ether, and R here is the carboxylate anion, and we see that this has got a threefold symmetry, and the guanidinium also has got a threefold symmetry. So these two are complementary to each other. the symmetry of the guanidinium, which is the the three-fold symmetry, is complementary with this particular three-fold symmetry. So now it can nicely go and sit in this pocket, and it can form the hydrogen bonds C N N N. So it can form the hydrogen bonds here, here. Okay. So we can see that the hydrogen bond exists now, and the positive charge is here, and these are the N plus H O hydrogen bonds. So this kind of a strong binding and complementarity exists between your guanidinium, and now instead of guanidinium you can also have the imidazolium cation, which can interact via hydrogen bonds, and in this case you will also have the CHO hydrogen bonds, which will play a role. So we have these very interesting interactions which are present here. Now we can go and look at the binding with lariat ethers. Binding with lariat ethers. So here also, what are lariat ethers? Let us look at different kinds of lariat ethers. Here it has been observed that for small size lariat ethers, as a function of the length of the side chain, because in the lariat ether we have got a side arm, irrespective of the length of the side arm, the magnitude of the equilibrium constant. So we will be looking at the values of log k, that is the log k values. The magnitude of the equilibrium constant does not change. However, for the large sized lariat ethers, it changes dramatically. So let us look at these values now. So when we have R N, so we have this lariat ether here, and R is equal to CH2OMe. So this is the side chain, and the length of the lariat ether can increase if it goes to CH2O3, and it goes to CH2O5Me. And now I am considering the binding with the ammonium cation, then this value is 3.06, 3.29 and 3.49. So here you can see that the binding is not very efficient here in the case of the lariat ether. It relatively remains constant. So increasing the length of this side arm does not really improve the magnitude of the binding constant. When we now go to so now when we increase the number of oxygens by 1, and there is a CH2 unit increase. Now when R is equal to CH2OMe, CH2O whole twice, whole thrice Me, whole 4 times and 5 Me. So we take these different molecules where the length of the side chain is increasing, and we take the log k values 3.14, 3.19, 3.38, 3.48 and 3.49. So you see that the magnitude remains constant. The magnitude remains constant. And so this was the second set of lariat ethers. This was the first set of lariat ethers, and now when you go to the next set of lariat ethers, so here you see that the number of oxygens is increased to 5, and now when you have R is equal to CH2OMe, then the magnitude of log K increases one order in magnitude, it becomes 4.2, and when it is CH2O or twice Me, it is 4.75. When it is 3Me, it is 4.56. When it is 4Me, it is 4.4, and then when it is 5Me, it is 4.04. So right away you can see that there is an increase in the magnitude of the log K value, an order of magnitude the log K value increases. The log K value increases by an order of magnitude. Now, why does this happen? And this is based on the fact that when you have an ammonium ion now present here, so when you have so you can see that we have got the hydrogens which are interacting with your hydrogen bonds. You can see that this is interacting with this, and however this hydrogen is in the vicinity of a CH2 unit. So there is a steric clash. Okay. So it is able to maximize the hydrogen bond. So we have these 3 hydrogens, and there are acceptors in the vicinity of 2 of these, but in this one it essentially encounters a clash with the CH2 group. On the contrary, when you consider this particular one, so here you will see that these hydrogens which are I am considering now in the plane, essentially these are a tripodal plane, they are able to form the hydrogen bonding interactions, but the one above say is here. So this is my ammonium cation now. So now you can see 3 of the hydrogens are able to interact with all the suitable acceptors. This is the 4th proton, and therefore it is able to bind more efficiently via the formation of this additional N plus HO hydrogen bond. So more is the number of favorable hydrogen bonds the ammonium cation is able to participate in with the suitable orientation and the arrangement of the acceptor atoms depending upon the size of the lariat ether, the more is going to be the magnitude of the binding constant, and this magnitude is not going to be changing too much if you change the length of the side arm or the length of the side chain. If it increases, you will see that it does not really enhance much the binding constant of this ammonium cation. So these lariat ethers also are a very good host to be able to encapsulate the ammonium cations. So overall in this lecture we have now seen at lariat ethers, corands and cryptands functioning as suitable host for efficient encapsulation of the organic cations. So now in the next lecture we will go to anions and see what are the factors which affect anion binding, what are the size requirements, what are the electronic requirements, the geometrical requirements of anions when it binds with suitable host, and what is the requirement on the host side as well to have efficient anion host binding. Thank you.